All right. Hello everybody and welcome to the next lecture of model engineering. Today we're going to talk about textual modeling languages. Concrete syntaxes improve the readability of our models. So in the previous sections we talked about how to define meta models, how to define the modeling language with a focus primarily on the abstract syntax. Yeah? While the abstract syntax is very important to define the expressiveness and the richness of our language and the valid models that can be created with that language, they are primarily not intended for humans. They are primarily intended for machines to understand the models to be expected and how to serialize and deserialize these models. However, when we aim that our models are also used and created by humans, then a textual or then a concrete syntax is of paramount importance. Yeah? And there's also a one-to-many relationship between abstract and concrete syntax. So one abstract syntax, one modeling language, meta model, can be kind of realized or represented by multiple concrete syntaxes, which enable us to do domain-specific or case-specific representations or visualizations of our conceptual models. So generally there are two types of concrete syntaxes. One is textual and the second one is graphical. They can also be combined, of course, and most often actually they are combined. And this will be the topics of today's and of the next lecture. So first we want to start talking about textual syntaxes, followed by a discussion about how to realize graphical concrete syntaxes. Generally, there can be, as already mentioned, several alternative notations or concrete syntaxes for one meta model. See the examples on the bottom here, where we have three alternative notations for the creation of an appointment, where the appointment relationship is either a border node or it's a rectangle on its own that has two relations, incoming and outgoing, or we can even have a textual concrete syntax in the alternative three. Yeah? When we talk about textual concrete syntaxes, we also should consider the formal definition of those syntaxes, because once we define the concrete syntax on a formal basis, this allows for automated generation of editors that can support the creation of models using that textual concrete syntax. And there are several approaches and frameworks available that we will discuss in the following for realizing this, particularly also in the EMF ecosystem. On a generic basis, what is very important is to understand the relationships between the meta model and the concrete syntax, so abstract and concrete syntax. The visual notation, as visualized in this schema on the bottom, symbolizes our meta model elements. And then if we go to the lower level, every model which is conforming to our meta model is then visualized using one diagram or text, depending on whether we have a graphical concrete syntax or a textual concrete syntax. And independently, this diagram or text conforms to the visual notation that we have specified. So what is important is that to some extent we need to map each element of our meta model to a graphical representation, to a concrete representation, either being a text or a graphical or shapes or a mix of both, but we need to define this mapping, and there are different ways of how to do that. If you look at the standards, we will see that many modeling languages don't go into any formal level of detail when specifying the concrete syntaxes. So albeit the fact that the meta models are very formally specified, when we consider the concrete syntaxes, most of the times in the standards, for example, look at the UML example here, they just use such a mapping table, where on the left-hand side we see the node type. So the node type is an element of our meta model, and then the notation is the visual element. So this is the mapping that I mentioned on the previous slide. But formality now relates not to the mapping, which is a one-to-one mapping here, but it relates to how we specify the notation. So if you see, for example, the initial node, it's a blue it's a circle that is filled with a black color. And this is not formal at all, because not even the color of black is formally specified. Also, the size of that circle is not specified formally. So any tool developer could realize a different black circle of different sizes. And the same, analogously, the same applies to the fork node, the join node, and the merge node. Of course, when the graphical concrete syntax gets even more complex, there's even more need to define formally a concrete syntax. And this is not only important that the models look the same or similar using different modeling tools. It's also very important for tool developers, because for tool developers, the ambition for them is to be conforming to the standard or conformant to the standard. But if the standard does not specify formally the graphical concrete syntax, the tool vendors need to interpret. So they need to decide how to realize the notation in the most appropriate way, which is, of course, why many UML tools, the models, if you create the same model in different UML modeling tools, to stay with the UML example, you will see that the models differ quite dramatically, because the concrete syntax is not formally specified. And this is, of course, not something that is intended and should not be. So generally, when we talk about concrete syntax, we also need to differentiate the abstraction level in our meta modeling hierarchy on which we want to create a graphical concrete syntax. First, we can talk about concrete syntaxes for meta models, which you should be already familiar with using based on the lab work that you have conducted in the previous weeks. So in the in the Eclipse EMF world, we can have the tree-based editor as seen on the right-hand side, where we have the abstract syntax, the meta model, represented in a tree-based structure. Likewise, in EMF, we can generate a graphical representation on the top right side, or also a textual representation on the lower right side, and both of which visualize or represent the meta model that has been specified in the tree structure on the left-hand side. So they are visualizations, and of course we can also work with the graphical editor and the textual editor to change the meta model. But the important message is here: concrete syntaxes can be positioned on the meta model level, so we define ways how to visualize the meta model itself, and also on the model level. So a model, of course, we know that conforms to a meta model, and then also on the model level we can define a graphical syntax. This is what you are used to when you use any modeling editor like the one shown on the upper right side, where you have a canvas and you can drag and drop elements there and you can combine them. But also a model can be visualized and interacted with using a textual syntax as shown on the lower right area, and that is the focus of today's course. So we will talk about how to realize a textual syntax for our model, for our meta model, and how to use that to create models in a textual manner. And of course also we will motivate why a textual syntax can be meaningful as a concrete syntax for our modeling language. So let's start with the latter part and start with the motivation. Why is a textual modeling language meaningful? So generally a textual modeling language can be defined by the equation that it is a meta model plus a textual concrete syntax. Yeah? So like we discussed in the beginning, we have still our abstract syntax specified by means of a meta model, and we now enrich this with a textual concrete syntax. The models that we create using a textual modeling language are then plain text files that conform to the grammar that we have specified in our meta model. And now the question is, why would you do that? Yeah, because textual languages have a very long tradition in computer science. Think about the general purpose programming languages, but also a multitude of domain-specific languages and programming languages like HTML, CSS, SQL, and Maven. So all of them are textual languages, and as software engineers and developers, we are very much used to working with a textual representation. Moreover, also based on the fact that a model using a textual modeling language is a plain text file, we have much better scalability. We can use any plain text editor to use to work and to edit the model, to look at the model, to edit it. We can use easy pretty printing, and color coding can be very nicely customized. And eventually also a very interesting aspect is that if the model is represented only as a text file, we can also relate on existing version management systems to do some version management of our models, which is not that easy when we talk about graphical models and how to keep track of changes in that model. There are two different ways of textual languages. Some of you might already be familiar with internal languages. They become very mainstream in languages like Ruby and Groovy and Scala. And these are the explicit languages, so where internal languages are explicitly specified and then used. Or there are also the means of implicit internal languages like the fluent interfaces that you might already know from Java and C#, where the interfaces and the APIs are designed in a way that the method calls and the classes are fluent and are speaking for themselves. So the idea here is to be more explicit and more bold in what is happening when I call a certain method, instead of having the semantics of the parameters only specified in the sequence of the parameters without explicit names. And the other alternative, of course, are external languages. They have their own syntax, they come with their own parsers to process them and own editors to use them. And of course, for those external languages, we need to define compilers and interpreters for executing them. And we will talk about that in the following lectures, how to realize such an external language by ourselves. For this, I want to reiterate on the extended Bacchus-Naur form, which is a very important and an ISO standard and very important standard to specify grammars in a very compact and very concise way. EBNF grammars consist of a sequence of terminal symbols like the Java keywords public, class, interface, package, and import. And EBMF specifies the valid combinations of the terminals by production rules. Yeah? And these production rules then define the grammar for the textual language in a compact and concise way, using a set also of predefined operators that we see here. So the production rules can be defined by the equation that a non-terminal is equals a sequence of terminals and non-terminals, and then we have some production rules to replace the terminals by non-terminals in a subsequent step. We will come to that example in just a few slides. For defining valid sequences of terminals, the following operators can then be used. So for example, you can define sequences by using a comma. You can define alternatives by using the vertical line. You can define repetition, optionals, and also groupings. And we will see how we use that in just an example that follows. The example relates to an entity domain-specific language. There's an example here where we have type string, type boolean, then we define an entity conference, which seems to have the properties of a name, attendees, a list of attendees, a list of speakers, a person which has a name, and then a speaker which extends the person with some different properties that are not closely specified on this slide. And if we now try to classify the different elements that we see here, we can see that we have some keywords like type, entity, property, and extends. We have some scope borders delimited by the brackets. We have separation characters by means of the double point. We have references and we have identifiers. So this is the first level of classification. And then we can use this classification and see how we can define an EBNF grammar that would allow to write to describe such an example. And the eBNF would then look like this. So we have a model which is a sequence of types. A type can be either, now we have the alternatives, a simple type or an entity. A simple type, and then we see the production rules here and how they are used. Yeah, a simple type can then be replaced by the notion of a type, and the sequence we follow it by an ID, and the identifier or ID is then the small and the capitalized letters and the numbers 0 to 9 and the dash. Yeah, so it gives us the full power of the alphabet to define any identifier for the type. An entity then has entity followed by an ID, followed optionally by extends, followed by an ID, and then come the brackets that compose a sequence of properties optionally. A property is then defined by property and an ID, a double point and another ID, and then optionally the corner brackets to indicate that there is a set. For example, as you see, property attendees, double point, person is then that second identifier, and then we have these brackets to indicate that this is a set of persons and not a single person. Now it's interesting to also relate this eBNF specification and compare it with eCore. So on the left-hand side we still see the eBNF specification that I briefly introduced, and on the right-hand side we would see kind of an eCore meta model that would realize more or less the same. So we say that the model is composed of elements which are types. Types have a name and can be specialized into a simple type and an entity. An entity can extend optionally a different entity, and entities are composed of 0 or many properties which have a name and can be singular or plural. Yeah? And now if we differentiate those two ways to specify a grammar, the eBNF way to specify a grammar and the eCore way to specify a grammar, we can say that eBNF is very good in specifying the concrete syntax, while eCore is very good in specifying the abstract syntax, but not talking at all about the concrete syntax. eBNF is very linear and has only limited reusability, while in eCore we have reusability by inheritance relationships. We have containment references and cross-references, and we can use predefined data types and user-defined enumeration. So we are much richer in the eCore world compared to the eBNF world because of those characteristics. From this we can conclude that a meaningful meta model cannot be generated from an eBNF grammar, and also vice versa. An eBNF grammar cannot generate automatically an eCore meta model. Yeah? And the question then is, of course, how to overcome this gap and what can we do with that. And generally there are two different ways or two solutions to that. We can only use a generic syntax where we use a generic serialization of the models like in XMI or in the human usable textual notation. So we don't care about concrete syntax because mostly the models are created and used by machines, and machines use the meta model to communicate with one another. Or the other alternative, we use a language-specific syntax where we can differentiate the meta model first approach. This is the approach that we follow in our class. So in the first part we specified the meta model, and now we are talking about the specification of the textual syntax. So we define the mapping when we already have the meta model and we come up with a textual concrete syntax. But there's also the other way around, where you can specify the syntax by means of a grammar, and then this composes the concrete and the abstract syntax, and the meta model can then be derived from that grammar. An example framework for realizing this is Xtext, which is a plugin to the Eclipse ecosystem, which we will also use in this course to actually define the textual concrete syntax for our meta model. That concludes the first introductory part on textual modeling language. Thank you for listening.